Welcome to the next session. Subject Engineering Maths. We were in chapter 3. We were discussing calculus. That is module 1, differential calculus of calculus. And the concept today is differentiability. Already in the last session we had a few things about differentiation. Let us continue some more issues about differentiability. We were in the discussion of examples. See, we have seen that in the last session, differentiability of a function f of x in closed interval a comma b. When do we say that f of x is differentiable in this interval? If f of x is differentiable at all points of this interval. If f of x is differentiable at all points of closed interval a comma b, then we say that f of x is differentiable in closed interval a comma b. What does it mean? F dash of x is finite. F dash of x is finite for all x belong to closed interval a comma b. So if this happens, then we say that f of x is differentiable in this interval. In the last session we have seen an example of constant function. Now let us continue examples. Example 2. Suppose I have f of x equal to e power x. So let us take the interval as closed interval minus 2 comma plus 2. Now f of x is equal to e power x in this domain. Let us verify its differentiability in this interval. What is the derivative of this? It is e power x only. Now replace x by any element of this interval. It is always finite. So e power x is finite for all x belongs to closed interval minus 2 comma 2. Therefore e power x is differentiable in closed interval minus 2 comma 2. As we know that the domain of exponential function is set of real numbers. Now here this is a subset of real numbers. It's a small set. Of course it has infinitely many elements, but it's a small set. So when you find the derivative of e power x, we are getting e power x. Replace x by any element of this interval. This is always finite. Therefore according to this definition, e power x is differentiable in closed interval minus 2 comma 2. Now example 3. Suppose f of x equal to a polynomial expression, or for example I can go for sin x in the domain closed interval, for example 2 comma 4. Now what is the derivative of this? The derivative of this is cos x. So we know that the domain of cos x is R. That means for all real values of x, cos x is finite. Therefore in particular this is finite even when x belongs to this interval. So this is finite for all x belongs to closed interval 2 comma 4. Therefore the function sin x is differentiable in closed interval 2 comma 4. Next example is cos x. F of x equal to cos x. Let us take the domain as closed interval 0 comma 3. Now what is the derivative of this function? The derivative of this function is minus sin x. Now we know that the domain of sin x is set of real numbers. That means this is a finite number for all x belong to this interval. So it is finite for all x belong to closed interval 0 comma 3. Therefore the function cos x is differentiable in closed interval 0 comma 3. It is differentiable in closed interval to 0 comma 3. Now as a last example we can take polynomial expressions. Suppose if I take f of x equal to x cube minus 3x square plus 4x minus 20. Say it's a third degree polynomial expression. This is a third degree polynomial expression. Now let us consider this function in the domain closed interval, for example minus 1 comma 4. Now when you differentiate this, the derivative of this is 3x square minus 6x plus 4. Now when you differentiate a third degree polynomial, the result is a polynomial expression of degree 2. So remember always one point, when you integrate a polynomial expression, the result is a polynomial but degree will be raised by 1. When you differentiate a polynomial, the result is again a polynomial expression but degree will be reduced by 1. So it is a polynomial expression. Now this is finite for all x belong to closed interval minus 1 comma 4. Therefore, the function x cube minus 3x square plus 4x minus 20 is differentiable in closed interval minus 1 comma 4. Minus 1 comma 4. Therefore, from all the examples, what we conclude is when you look at polynomial expressions, just as we have seen in the last case, polynomial expressions, exponential functions, sin x, cos x, constant function, all these functions are differentiable in every closed interval a comma b. So they do not have any drawbacks in terms of differentiability as well as continuity. Okay, so make note down all these examples. Just note down the point. All polynomials, comma constant functions, all polynomials, comma constant functions, comma sin x, comma cos x, and e power x, are differentiable in every closed interval a comma b. All polynomials, comma constant functions, comma sin x, comma cos x, and e power x are differentiable in every closed interval a comma b. Next topic, properties of differentiable functions. Properties of differentiable functions. In one of the previous sessions, we have seen properties of continuous functions. Same properties will work even for derivatives also. Suppose I have two functions f of x comma g of x. Assume that both are differentiable at the point A. Functions are different but both are differentiable at a common point A. Then property 1 is f of x plus g of x is also differentiable at A. So that means sum is always differentiable. Now replace plus by minus, that is f of x minus g of x is also differentiable at the same point A. Now replace this minus by dot multiplication. F of x dot g of x is also differentiable at the point A. Now when you look at ratio, here the problem comes. F of x by g of x. This f of x by g of x may or may not be differentiable at A. May or may not be differentiable at A. So therefore, since the result is negative, in order to prove this, at least I need one example. As we seen in one of the previous sessions, as properties of continuous functions, sum is always continuous, difference is always continuous, product is always continuous, ratio may or may not be continuous. So all these properties are valid even for the concept differentiation. Sum is always differentiable, product is always differentiable, difference is always differentiable, but when you go through ratio f of x by g of x, it may be differentiable, may not be differentiable. So I give one example. Such examples are called counter examples. Let us see what is the counter example for this. The counter example is f of x equal to 1, g of x equal to x. Now this is a constant expression, this is a polynomial expression. Both are differentiable at all points. In particular, they are differentiable at a equal to 0. Now when you look at its ratio, f of x by g of x, this is 1 by x. This is not differentiable at 0. This is not differentiable at 0. Because when you differentiate this, the result will be minus 1 by x square. Of course, 1 by x, it does not exist when x is 0. So the function has no meaning when you replace x by 0. Ultimately, it has no derivative. Therefore, the ratio need not be differentiable. This is one of the best counter example. Okay. So note down these points. Next we discuss a relation between differentiable and continuous functions. Relation between differentiable and continuous functions. Let us see. Now we have two concepts for a function at a point. One is differentiation, another is continuity. Let us see how the relation looks like among these functions. So we have a function f of x. A is some real number. We have two concepts. One is differentiation, another is continuity. Now the relation between these two is, if something is differentiable, if a function f of x is differentiable at a point A, implies it is automatically continuous at the same point. D implies C. That means all differentiable functions are continuous at those points. If f of x is differentiable at a point A, implies f of x is continuous at the same point. Now, what is the converse of this statement? See, whenever we have some statement, we need to discuss its converse. Converse is nothing but C implies D. C implies D. So this may be true in some cases, may not be true in some cases. So what do you mean by converse of this? Do you feel that all continuous functions are differentiable at all points? Certainly the answer is not. Let us see. Suppose I have a function f of x equal to, I am giving counter example, f of x equal to modulus of x minus 3. We know that modulus of x minus k is continuous at all points. In particular, this is continuous at 3. This is continuous at 3. But f of x is not differentiable at 3. But this is not differentiable at 3. So this is the best counter example. So converse of this statement need not be true. That is, all continuous functions may be differentiable, may not be differentiable. This is the best counter example. F of x equal to modulus of x minus 3. See, we have seen the graph of this function. It is always continuous. In particular, it is continuous at the point 3 also. It is continuous at 3 also. But the drawback of this function is 3 in terms of derivative. So it is continuous at 3 but not differentiable at 3. Now the point number 3 is, if f of x is not continuous, implies f of x is not differentiable at the point A. So these 3 points are very, very important. First relation is all differentiable functions are continuous at all points. Second one is its converse. Converse may or may not be true. This is the best counter example. Modulus of x minus 3. It is continuous at 3 but not differentiable at 3. Because the drawback of this function is 3 in terms of derivative. But there are no drawbacks in terms of continuity. Now third point is, if something is not continuous at a point, ultimately it is not differentiable at the same point. So this is always true, 100%. This is always true. But second point may or may not be true. That depends on example to example. Okay. Note these points. Point 1. If f of x is differentiable at a point A, if f of x is differentiable at a point A, then f of x is continuous at A. If f of x is differentiable at a point A, then f of x is continuous at the point A. Second point, the converse of above may or may not be true. The converse of above may or may not be true. That is, if f of x is continuous at a point A, if f of x is continuous at a point A, then f of x may or may not be differentiable at A. Then f of x may or may not be differentiable at a point A. Counter example, f of x equal to modulus of x minus 3. F of x equal to modulus of x minus 3 is continuous at 3, but not differentiable at 3, is continuous at 3 but not differentiable at 3. Now point number 3. If f of x is not continuous at a point A, if f of x is not continuous at a point A, then f of x is not differentiable at the point A. If f of x is not continuous at a point A, then f of x is not differentiable at a point A. I think all these points are very clear. Now, let us focus on point number 1. All differentiable functions are continuous. Now, if you want to prove that, or if you want to verify that a function is continuous at a point or not, we have 3 alternatives. One is by using limit concept. Yes or no? If you want to say that a function f of x is continuous at A, you must prove that limit exists at that point and that value must be equal to functional value. That is one possible way. Second possible way is its graphical representation. Third way is its derivative. So if you are unable to find its limit, or if you are unable to draw the graph of a complicated function, still you can prove that it is continuous by discussing its derivative, right? So therefore, this is one of the powerful tool to say that f of x is continuous at one point, right? Now we discuss mean value theorems. We have 3 mean value theorems. Let us discuss one by one. The first mean value theorem is Lagrange's mean value theorem. Let us see what this theorem says. Suppose we have a function f defined from closed interval AB to set of real numbers R. So here the domain of the function is closed interval A comma B, codomain is R. So assume that this function satisfies 2 conditions. The first condition is f of x is differentiable. So we need to start with continuity. Okay, let us take differentiable. So it is a differentiable in open interval A comma B. And second one is f of x is continuous in closed interval A comma B. It is differentiable in closed interval A comma B and continuous in closed interval A comma B. So whenever a function f from this to this satisfies these 2 conditions, then at least at one point in this interval we can able to say derivative easily. Here I am saying that it is differentiable in open interval A comma B. So here A is not included, even B is not included, but at all points in between A and B, the function has a finite derivative. That's why we are saying that it is differentiable in open interval A comma B. So that means if you take A value 2, B value 3, or when you take f of x between open interval 2 comma 3, what does it mean? F of x has a derivative at all points above 2 and below 3. So therefore, f of x has derivative at all points in between open interval A comma B. And we know that the graph of f of x is continuous in closed interval. Remember 2 points. For continuity, closed interval is required. For differentiability, endpoints may not be required. Even if you don't have derivative at A, no issues. Even if you don't have derivative at B, no issues. Even if you have derivatives at A and B, you don't get any additional advantage. So you need not worry about endpoints regarding derivative. It must be differentiable in open interval and continuous in closed interval. Since I am saying that the function has a derivative at all points in between this interval, at least at one point in this interval, I am going to write the conclusion. Then at least at one point, say C in open interval a comma b, comma f dash of C equal to f of b minus f of a divided by b minus a. This is the conclusion of Lagrange's mean value theorem. So then at least at one point, say C in open interval a comma b, the derivative looks like this: f of b minus f of a divided by b minus a, right? I will tell you one example. Suppose f of x is a function which is continuous in closed interval 2 comma 3. Assume that this is differentiable in open interval 2 comma 3. Then since I am saying that it has a derivative in open interval 2 comma 3, so f dash of 2.1 is finite one because 2.1 belongs to this interval. F dash of 2.2 is a finite number because it is differentiable in this interval. If you continue up to like this, f dash of 2.99. So therefore, function has a derivative at all points above 2 and below 3. All these values are finite numbers. That is the meaning that f of x is differentiable in open interval 2 comma 3. But I don't know what is f dash of 2.1. I know that it is finite value, but I don't know what is that value. The same case with the rest of the values also. It is a finite number. This is finite, and all these values are finite, but we do not know unless or until we calculate these values. Therefore, Lagrange's mean value theorem says that at least at one point in this interval, for example, C belongs to open interval 2 comma 3, the derivative of the function looks like this: f of 3 minus f of 2 divided by 3 minus 2. So this is the conclusion of Lagrange's mean value theorem. Okay, very, very powerful point. Note this. Let f from closed interval a b to r. Let f from closed interval a b to r be a function. Let f from closed interval a b to r be a function such that point number 1, f of x is differentiable in open interval a comma b. F of x is differentiable in open interval a comma b. Point number 2, f of x is continuous in closed interval a comma b. F of x is continuous in closed interval a comma b. Then at least at one point, say C in open interval a comma b. Then at least at one point, say C in open interval a comma b, comma f dash of C equal to f of b minus f of a by b minus a. F dash of C equal to f of b minus f of a by b minus a. So basically derivative is a slope. So this is y2 minus y1 divided by x2 minus x1, right? So here what this f dash of C, this basically represents slope of line joining the points, a comma f of a comma b comma f of b. Just you assume that these are x1 y1 x2 y2. You find the slope y2 minus y1 divided by x2 minus x1. Therefore here f dash of C is a slope of the line joining the points a comma f of a and b comma f of b. Note here f dash of C represents slope of line joining the points. Here f dash of C represents slope of line joining the points a comma f of a and b comma f of b. A comma f of a and b comma f of b. Okay. Now we discuss examples. Once we go through examples, you can understand why they are called mean value theorems. Basically, mean is nothing but midpoint or average. So you can understand easily by discussing few examples. Okay. Now let us discuss examples of Lagrange's mean value theorem. So let us see examples. First one. Suppose we have a function f of x equal to x square plus 9 in closed interval, for example 2 comma 4. Now let us verify mean value theorem for f of x equal to x square in closed interval 2 comma 4. Verification. See, what do you mean by verification of Lagrange's mean value theorem? We need to verify that whether this function fulfills both the conditions of Lagrange's mean value theorem. Once this function fulfills both the conditions in this interval, I need to find f dash of c and make sure that c belongs to this open interval 2 comma 4. Now let us see. Here the first condition is f of x equal to x square plus 9. This is a polynomial expression. We know that all polynomials are differentiable in all intervals. In particular, this is differentiable. This is differentiable in open interval 2 comma 4 because for derivative open interval is enough. Now when you go to continuity, f of x equal to x square plus 9 is continuous in closed interval 2 comma 4 because all polynomials are continuous and differentiable in all closed intervals. So it fulfills both the conditions of differentiability and continuity of Lagrange's mean value theorem. Therefore, by Lagrange's mean value theorem, there exists c belongs to open interval 2 comma 4 such that f dash of c equal to f of 4 minus f of 2 divided by 4 minus 2. So by Lagrange's mean value theorem, we get there exists c belongs to open interval 2 comma 4 such that this will be happened. Now what is f dash of c? So the derivative of this is 2x. F dash of c is 2c. What is f of 4? 16 plus 9, 25. F of 2, 4 plus 9, 13. So divided by 2. Now this implies 2c equal to 12 by 2. So this is 6. Therefore c equal to 3. Now this belongs to open interval 2 comma 4. Interestingly, this 3 is nothing but midpoint of this. Therefore this 3 is actually mean of the interval 2 comma 4. Mean of the interval 2 comma 4. That's why they are called as mean value theorems. But don't expect c value always midpoint of interval. In this case it is happened, but in most of the cases when you take any example, that c value will be very close to midpoint. So for the same problem, when I change domain, again c will be midpoint. So when you look at the small example x square plus 9 in this interval, it has fulfilled all requirements of mean value theorem and we were getting c value 3, that is the midpoint of this interval. Midpoint is nothing but mean. So therefore at mean we can easily get the value of derivative. That is c is nothing but, in almost all cases c is mean value. Let us discuss few more examples. We get some clarification about c. So first note down this example. Now we discuss example 2. Let us generalize the second degree polynomial. It is a particular second degree polynomial expression. Let us handle general second degree polynomial expression. I call it as Lx square plus mx plus n in closed interval a comma b. So here L is not equal to 0. That means here the coefficient of x square is L, it is non-zero. So what is my meaning is, here this is a second degree polynomial expression. So we don't know the value of L, M, N, but L is non-zero. So it's a second degree polynomial expression. So interval is general interval a comma b. So here f of x is differentiable in open interval a comma b because all polynomials are differentiable in all open intervals and all polynomials are continuous in all closed intervals. So f of x is differentiable in open interval a comma b, and f of x is continuous in closed interval a comma b. Therefore, by Lagrange's mean value theorem, there exists C belong to open interval a comma b such that f dash of C equal to f of b minus f of a divided by b minus a. So this implies, what is f dash of C? Derivative of this is 2lx plus m. So derivative is 2lc plus m equal to f of b. This is lb square plus mb plus n minus la square plus ma plus n divided by b minus a. Therefore, 2lc plus m equal to nn will get cancelled. This is l into b square minus a square plus m into b minus a divided by b minus a. Now you can cancel out b minus a here. So you will get 2lc plus m equal to l into b plus a plus m. So this m will be cancelled. So LL will be cancelled. So C equal to B plus A by 2. Therefore, in this case, the value of C is B plus A by 2. So finally, we got C value equal to B plus A by 2. Anyhow, this belongs to open interval A comma B, and this expression is mean of the interval A comma B. So that's why when you take any general second degree polynomial expression, in every interval, its C value is always mid value. So even when you take third degree equations, fourth degree general expressions, that C need not be exactly midpoint, but C will be very close to mean value. Let us handle that in example 3. So you can note down this as a general second degree polynomial expression. So C value is midpoint. Note the value of C of Lagrange's mean value theorem. The value of C of Lagrange's mean value theorem for all second degree polynomials. The value of C of Lagrange's mean value theorem for all second degree polynomials is always midpoint of the interval. Okay. Now let us take a different example. Last example 3. Suppose I have f of x equal to, for example, x cube plus 4. Let us discuss its mean value theorem in the interval closed interval 2 comma 4. Interval is same as previous, as example 1, but function is third degree polynomial expression. Now it is continuous in this interval, and even it is differentiable in this interval. Continuous in closed interval 2 comma 4. Differentiable in open interval 2 comma 4. Therefore, by Lagrange's mean value theorem, there exists C belongs to open interval 2 comma 4 such that f dash of C equal to f of 4 minus f of 2 divided by 4 minus 2. So this implies, what is f dash of C? 3c square. So 3c square equal to f of 4 cube, 64 plus 4, 68 minus f of 2 cube, 8 plus 4, 12 divided by 2. So this implies 3c square equal to 68 minus this 12. So it is 56 by 2. So this is 28. So therefore c square equal to 28 by 3. So basically this is 9.3, for example 9.33, something like that. So c equal to square root of 9.33 plus or minus. We get two values. One is with plus, another is with minus. But negative values should not be there in open interval 2 comma 4. Therefore, C value must be, so square root of 9.33. So this is approximately 3. Approximately 3. You can see C value is almost close to mean of this interval. So even if you take any polynomial expression, even any general trigonometric function, even though you need not get C value, mean value, but C will be very close to mean value. Okay. So this is the proof, not this point. Just mean value theorem. Now we move to second mean value theorem. So second mean value theorem is Rolle's mean value theorem. Now basically this is a particular case of Lagrange's mean value theorem. Suppose we have a function f from closed interval a b to r such that f of x is continuous in closed interval a comma b, f of x is differentiable in open interval a comma b, continuous in closed interval, differentiable in open interval a comma b, and third condition we have is f of a equal to f of b. So that means function must take same values at the endpoints. Function must take same values at the endpoints. F of a, functional value at a, functional value at b. So function takes same values at the endpoints. In case of Lagrange's theorem, we don't have this condition. So if I don't have this condition, what will be my f dash of c? My f dash of c equal to f of b minus f of a divided by b minus a. But in case of Rolle's mean value theorem, we have the condition f of a equal to f of b. So replace f of a by f of b, then you will get f dash of c equal to 0. Therefore, this is the conclusion of Rolle's mean value theorem. So whenever these three conditions happen, then at least at one point c in open interval a comma b, the derivative of a function is 0. At least at one point c in the open interval a comma b, then the derivative becomes 0. Not this. Let f from closed interval ab to r, let f from closed interval ab to r be a function such that point number 1, f of x is continuous in closed interval a comma b, f of x is continuous in closed interval a comma b. Second point, f of x is differentiable in open interval a comma b. Point 3, f of a equal to f of b, f of a equal to f of b. Then at least at one point c, in open interval a comma b, at least at one point c in open interval a comma b, comma f dash of c equal to 0. At least at one point c in open interval a comma b, f dash of c equal to 0. Right? Now we discuss one example. So here f of x is sin x in closed interval 0 comma pi. Now let us verify Rolle's mean value theorem in this. So we know that all trigonometric functions, particularly sine and cos, we should not take tan, cot, etc. So particularly when you take trigonometric functions like sine and cos, it is continuous in closed interval a comma b. So sin x is continuous in closed interval 0 comma pi, and sin x is differentiable in open interval 0 comma pi. Now what is f of a? f of here a value is this. A value is 0 and b value is pi. So we need to verify third condition. F of 0 is sine 0. It is 0. F of pi, that is f of b, sine 180 degrees. This is also 0. Therefore, here f of 0 equal to f of pi. Therefore, it fulfills third condition also. So, therefore, by Rolle's mean value theorem, by RMVT, Rolle's mean value theorem, there exists C belong to open interval 0 comma pi such that f dash of C equal to 0. Now, what is the derivative of this function? Cos x. But the derivative at C is cos C. Cos C equal to 0. So, this equation have infinitely many solutions. For all odd multiples of pi by 2, see, you can take C value pi by 2, 3 pi by 2, 5 pi by 2. For all odd multiples of pi by 2, the value is 0. But you must consider C value which belong to this open interval a comma b. So, the value of C is pi by 2. Of course, this belongs to open interval 0 comma pi, and even this pi by 2 is midpoint of this interval, midpoint. You can see even in case of trigonometric functions also, we were getting C value as midpoint of the interval. Okay, note this. Now let us discuss one more example on this, and then we move to the next mean value theorem. So second example, suppose f of x equal to x square plus 1 in closed interval minus 1 comma 1. So second degree polynomial, it is continuous in closed interval minus 1 comma 1, differentiable in open interval minus 1 comma 1. So f of minus 1, a value, b value, f of minus 1 is 2, even f of 1 is 2. So function takes same values at the endpoints, that is f of minus 1 equal to f of 1. Therefore, there exists C belong to open interval minus 1 comma plus 1 such that f dash of C equal to 0. The derivative of this is 2C. C equal to 0, so this is 0. In fact, C belongs to open interval minus 1 comma plus 1, and this is mean of open interval minus 1 comma plus 1. So here also we were getting C value as mean of open interval minus 1 comma plus 1. Note this. Anyhow, this is a second degree polynomial. So even in case of Rolle's theorem also, we were getting C value as midpoint of open interval a comma b. Note this.